Okay, in the interest of time, we should probably get started. I think more people will probably filter in and out, but it's a great pleasure of mine to introduce a good friend, Dr. Kai Hoeffner, who's he's a process engineer in the Bioprocess Engineering and Data Analytics group at Sanofi Genzyme. Before that, I had the pleasure of working with him at MIT in Professor Paul Barton's lab. He also worked in healthcare, in various healthcare technology in the Max Planck Institute in Magdeburg, as well as when he came back to the States, working at Mass General before taking his position at Genzyme. At Genzyme, he supports process development, scale-up, and tech transfer of cell culture processes across their biologics platform. And he received his PhD in chemical engineering from Queen's University in Kingston, Ontario, and the diploma in engineering and cybernetics from the University of Stuttgart. So he's worked across a number of different applications and platforms in systems engineering, and now he's doing quite a lot of work in biopharma processes. So I'd like to welcome to give your seminar, and look forward to your talk. Thank you.
Thank you, Matt. Thanks for the invitation. Hello, everyone. Matt mentioned my background is basically in systems engineering and different aspects of it. And what I would like to share today is basically a systems perspective of problems challenges and opportunities that we see in bioprocess engineering, and in particular in biopharma. So, I don't know how many people are familiar with the biopharmaceutical industry, so I just want to give you a broad overview. Maybe some of you know basically how drug development works. So usually if you look at drug development, you have if you have a drug of interest, a target. So we're looking right now in the biopharmaceutical, so that means that the product, the medicine is produced by biological means, so not by chemical means, like aspirin, but by biological means, so antibodies and other things where cells produce actually the drugs that are being used. So usually how you start in this life cycle for the product is you start with toxicity. So once you have a target, you check if it has toxicity that's basically safe to be used in humans. And then you have the phase 1, phase 2, phase 3 trials. So basically you start with healthy volunteers where it's tested on safety and there's safe use. Then you step up. So these are just a small number of volunteers to check that. Then you increase the number of now going to patients, and you check for efficacy and also safety. And once this passes, you go to phase 3 trials, which is the big one, where you show that you have efficacy, effectiveness, and safety. And once you're done, basically what comes next is you have a filing, you file to the FDA, you present all your results. And if that goes well, you can bring that product to market, basically. And then you have to manufacture it and supply the market. Some products, it's important for your market to have that. For other products, it's really important for the patient because it's a life-saving drug, so you have to make sure to supply that drug in adequate supply. So that's the usual development from a drug perspective. So this is how you would see it from a clinical side of view. So as an engineer, at the same time you have to do scale-up, right? So you have, first of all, not only have to have this drug, but you also have to produce it. So for biologic, that means you have to have a bioreactor where you grow your cells and separate the product out and refine it to get your final drug substance. And so in the second part here, so parallel to the clinical development, you have the development of your process that produces this. Again, you're starting off with this simple bench scale process, shake flask, something like this, where you get your first results, where you can supply some supply basically for your first 2 phases of the clinical trial. Then you have to understand your process better and exactly be reproducible in the way you produce your products, because it has to be reproducible as a final drug product. And you also have to scale up your product. So you have more patients now that you need to supply, depending on your clinical trial, for a longer time. So you also have to produce the product in a bigger scale. That will continue. Then you need a process qualification. So that means you have adequate state of control of your process that you can guarantee you for the quality attributes that you have described to your product can be reached every time. You need documentation. You need to be in what's called good manufacturing practice, the GMP environment. You have to establish all that for your process. So there are more and more requirements set on your process. Then you get to the biologics license applications, which is in line with the filing that you're doing, basically showing that you have a process that is reproducible, that really gives you the desired product. And then once now this is, again, depending on what kind of your blockbuster, you have thousands of people that you now need to supply. Basically, now you have to ramp up your production to thousands of liters potentially from a bench scale. So your process development also has to go together with the product that you develop. And while you're doing this, basically you have to have then process monitoring, make sure that your process is working correctly. And as you're continuously learning about your process, you have continuous improvement, adapting your process, making it better, making it more robust. So as a bioengineer or a biosystems engineer, basically one big part of the organization is the manufacturing science and technology part, which supports this, starting at process qualification a little bit earlier already, this process development and the manufacturing approach. Basically, how to better understand and characterize and control the process. And that's what our group is basically part of, the manufacturing science and technology department, and does the bioengineering and data analytics. And this, as I already mentioned, looking at monitoring, understanding, and control manufacturing operations and tech transfer. So in general, what you would, in the larger sense, also describe as systems engineer. Right? You have a really in-depth understanding of your systems, and you know how to control it. And it doesn't really matter if it's electrical engineering, mechanical engineering, chemical engineering. It's just a different application of this. So, in terms of the bioprocess engineering applications within this life cycle of the process, there are different ways. So all of this is around process understanding, as I said before. And usually, if we have the possibility to get from the learning that we had from existing processes, we try to give our input into process design. So if a new process is being designed, how can we make this better? So this is early stage on. Then I'll go into this into more details. A lot of times, while a process is being developed, it's not being developed at one site from one team. So it will be transferred from one side to another side, from one team to another team. And as I said before, during the development of the drug, it also has to be scaled up. So it's a lot of scale up and tech transfer. And then once it's in production, so it's in a GMP environment, every deviation of the set of controls that you set in place during the filing will lead to deviation that needs to be investigated, and there needs to be a corrective action and corrective and preventive action taken to correct the deviations that happen or prevent it from happening again. So basically it's also, again, center of process understanding, and that's where bioprocess engineer or systems engineer actually comes in and helps manufacturing to make this process better. And that leads ultimately then to process improvement because you have accumulated that kind of knowledge. So that's what our group is basically doing. I know not all of you are familiar with bioprocess engineering, so basically just from a technical point of view, what it means for a manufacturing process for biologics, how it works. So basically you start off with a frozen vial of cells. So in most cases these are CHO cells that are specifically modified to produce the the monoclonal antibody or a protein of interest. So you have the cell, and you know that's producing the product that you want. So then you follow this vial, and then you have only a few cells, so you need to scale this up because you want to produce this in large quantity. So you have several steps of smaller and increasing the bioreactor and increasing size, where the cells multiply and increase in numbers. When you get to what is called the seed, this is the whole seed train basically, until you have enough volume and enough cells to inoculate your production bioreactor, in which the cells further grow and then usually express the protein of interest. Then you harvest this by separating out the cells, the protein of interest, and keeping the cells in the bioreactor, or if you're in a batch operation, basically you just terminate this and then get to do this. So basically this can be run in a batch mode or in a continuous mode. And then you have different chromatography steps where you now try to isolate your protein of interest and purify it. So you have chromatography and phosphorylation steps until you get a purified product. You finish it, and then it's usually can be shipped to the patient. So what we're going to focus on is the cell culture part, so mainly the cell bioreactor and how this is, what challenges do we have there, and how this can be addressed with the systems approach. So, as you can imagine, this is a large-scale bioreactor. You have cells in there, you have everything else you have in a normal chemical reactor as well, so it's a complex and dynamic systems. These things can run for several months and have to be stable over this time. There are lots of changes in the cell's metabolite during that time. All of this leads to a complex and dynamic system. And as I mentioned before, one of the big practical challenges is basically that you want to produce the same product. Doesn't matter if you produce it in a 1 liter bioreactor or in a 10,000 liter bioreactor, right? You just want to have a different quantity of product, but you want to have, these are not the same. Just from an engineering or physical point of view, all these things are not scale independent. So we have to deal with how you change your process to make a scale independent product with a scale dependent process, basically. And furthermore, basically in terms of system understanding, electrical engineering, there are lots of components that are very, very well characterized. We can do mathematical models for all of them. We know exactly how they react. Same for mechanical systems, and to some extent for chemical systems. But for biological systems in this complex environment, there is no real good and reliable model currently available. There are different models in system biology that are used on like smaller scales and in different aspects, but to do this in a whole engineering application, there's still room for improvement. So the second part of my talk, I'm going to talk about work that I've done actually. So this first part will be on the work I've done or I'm doing in Sanofi right now, and the second part is part of the work I've done at MIT and Max Planck, which is a little bit more on the research side. So the first part, so applications of bioprocess system engineering. First, I'll talk about in a little bit detail of first principle models for scale-down models, and then computational fluid dynamics, how this can be used also for tech transfer and scale-up and scale-down. So as I said before, usually the normal process, you scale up a process. You start from a small-scale bioreactor where you develop in the lab and you scale it up. But as the requirements of the process become more stringent, because you want to have a consistent process, while you're doing this, you want to develop a way to test and understand this process in a large scale without having to run large-scale bioreactors the whole time. So one part of this, going around this, is basically having a qualified scale-down model. Once you're at a larger scale, you want to have something small you can run in the lab on different conditions, do a DOE, look at different things, because you want to analyze how changes impact your product, basically. So basically for this, you will want to have a qualified scale-down model. Okay? And qualified means that you can guarantee the same product quality attributes for this. So you produce the same kind of drug in the small scale as in the large scale. and they're similar but not necessarily identical in key performance indicators. So basically, you want to have the same per volume amount of cells, same viability, same titer of your product, something comparable. If you want to achieve this because of the scale difference, you can't achieve everything at the same scale, but you want to guarantee that you have the same product qualities. As I mentioned here, so basically mixing, mass transfer, gassing, and so on are all scale-dependent process characteristics, right? So if you want to scale something from 10,000 liters to 2 liters, mixing will be different. The amount of gas you need to control your oxygen or your pH or so on will be different. So all these things you have to figure out how to do this, and one way it's done a lot of times, basically if you want to do this experimentally, you still have to run only small-scale reactors, you still have to do a lot until you get to the point where you actually can achieve the same product quality. So one thing that we've worked on is basically developing a simulation model of the small-scale and the large-scale model to be able to confidently predict what kind of conditions we'd use in the small-scale model to do this with the least amount of experiment in the small-scale model to get close to a qualified scale-up model. So this is one of the case studies, basically. This is given, so we're at the point where we had a tech transfer from one side to another side. We had a large-scale model, and we wanted to qualify a small-scale model. So this is here, this is normalized pH. So this is around set point, and then PCO2. And we observed, so we ran this in a small scale several runs, and we observed that there's a difference in quality attributes. Quality attributes are usually charge variants, aggregates in your product, or changing glycosylation profiles. So basically, the cells behave differently, and they put different endings to your protein, so they don't exactly look the same way and don't have the same way of operating as you intended it to be. So there's some differences in the product quality, and there are some indications that these differences can be explained by differences in pH or PCO2 profile. So now the goal is basically to get the pH and PCO2 profile as close as possible to the large scale to get the same product quality profile. In this case especially, it was clear that in the first part of this batch was like a 2-week batch, that the change in pH and PCO2 early on in the batch basically had a big impact on the product quality. So we wanted to get this, so the GMP means the large-scale bioreactor, wanted to get this pH and PCO2 profile of the small-scale bioreactor closer to the large-scale bioreactor. And the obvious way of doing this is trying to adjust the pH and PCO2 by changing part of the gassing strategy since pH and PCO2 are coupled by the ionic balance, so if you want to change one, you'll also change the other one. So we're trying to get both closer together by basically adding CO2 to get this closer. And we want to get this done first time right, basically. So this was the first test. So we developed a simulation model. So basically, this approach. We identified product quality attributes and how they relate to the KPIs, and then use a first principle model, so basically engineering principles together put into a complex dynamic system to simulate this, optimize the parameters, so change the parameters to get the profile that we want in the simulation model, and then verify experimentally. And we actually got this pretty good, so it is sufficiently close so we could move on. So the model that we're using has been developed over several years. So I'm not the first one working on this. It's called cell culture simulator, but it's basically combinations of different aspects of the whole cell culture process. Basically, you have normal mass balances that you know from standard chemical engineering courses, with gas phase and liquid phases, with your cells in there. Then, so this is the essential part then what you also need, because again you want to predict pH, PCO2 and how they interact. So you need gas and liquid mass transfer, so you need to know the gas transfer coefficients at different agitation rates, different spark gassing rates, how your bubble composition changes over time and over space as well. And also, basically, there's a headspace, which also leads to mass transfer from the headspace into the liquid. And ionic balance, obviously, because you have this interrelationship. In addition to that, you have a buffer capacity that changes over time, and you have metabolites like lactate, which also have impact on your pH. So all these things are very, very dynamic and very interactive. And then your metabolite model, which in a simplest form is just the monode growth kinetics, but you can extend this depending on if you have inhibition, non-inhibition factors, and so on. And then this model also, so it's a process model, so it does not only the process itself, but also the feedback loops to control the whole process. So we can do basically simulation of the whole closed-loop process.
Question. So can you go back to the previous? So it seems like you have a lot of knobs to change, and if you're, I'm guessing that there is one true model, and all the other models used for other processes are probably descendants of that particular model.
Yeah, all parameterized.
And so how do you arrive at which or what are the particular parameters for a particular knob, so that it accurately represents this particular process as opposed to others? So how do you validate whether the changed parameter values actually correspond to the experimental results or the system that you're trying to actually model?
So we do an experimental validation from the simulation.
And is it directed? As in, is there, what I mean is there an exchange of information from this? Is something extracted from the model, and an experiment is devised so as to obtain these particular values, or is it kind of ad hoc, as in we fix a particular parameter, we test it, and then we refine the values one after the other?
So most of the parameters are basically derived from independent experiments that are basically, so this gas liquid mass transfer are like separate cell-free experiments where you identify the KLA basically. Then based on that, there are not a lot of parameters here. This ionic balance, you can analyze the media that you have, you can make the titration curves. So from that, you have part of their composition. So you get most of the parameters out there. There's one or two left basically. With all that in existing runs, you can estimate the metabolic parts, and then you're done. So basically, it's a combination of pre-existing data, doing some in-between estimation, and just engineering knowledge, basically. Okay.
Mm-hmm.
Yeah, basically, this is gas liquid mass. So basically, this is a spatial discretized model. So basically, it has the bubble rising over the spatial domain. So a relatively detailed model. And then the KLA measurements, basically, so you have the standard model of thin film model. So you do this cell-free model, and then you do measurements basically in on-gassing, off-gassing experiments with O2 or air to get your KLA. So you have dynamic response, which you use to estimate the gas transfer coefficients, basically. And you do that, so it's full DOE actually, to get full representation of your process model. Because this is something you would usually not do just for this particular question, but once you have that knowledge, whenever similar questions come up, you have all these parameters already identified. So yeah, this is something that we've done. And then, initial conditions. So basically, this goes through a list of the other parameters, right? The initial conditions are based on the experimental data that you have, buffer capacity, and are based on vendor information and some some prior knowledge. For the OUR, basically, once you have that, you can calculate back from your simulation what the OUR would have to be to give you the control input, the gassing strategy, gassing of oxygen to get you to steady state. So you can calculate back what your oxygen uptake rate would have had to be. So that's one way of identifying that. And then basically the feedback control settings you have from your system. So you can use that to simulate that. And with that, basically you can get pretty close. Again, it's not matched perfectly, but again, this is not, it's an empirically built model. It has a lot of information there, lots of engineering knowledge in there, but it matches it sufficiently well. Basically, you represent this characteristic dip in the pH control. EO control is obviously easily achieved, and the gassing profile is also fit, and the PCO2 profile matches, which also tells us that we have the right battle capacity and correlations between pH and PCO2. So we use that as a validation run. Okay. And then basically, once you have that model, now you can just look at scenarios. So you could do a full-fledged dynamic optimization or something like this, but in this case, it was just a simple question of how can we get this profiles closer. And one of the simplest things is basically to test out is to add CO2 into the overlay. Basically, increasing CO2 in the overlay will increase initially your CO2 in the liquid. In the first part, basically, we'll bring this up here. That was already before down there. And then also that 10% was basically tested out to get you close to the manufacturing scale to have this dip in the first 3 days. And then basically this is also a change that you cannot observe afterwards, but basically because of changing feeding strategy that you observe this going up. So with this, basically we get the simulation model close to the large scale, and then we implemented that basically that approach with 10% CO2 overlay, and we got this result that we had this characteristic dip and going up, and the PCO2 profile also matched, and from that we got the corresponding match of the very close match of the quality attributes for that scale-up model. So yeah, that's and there were no other impacts in terms of cell culture or titer and so on, so that was satisfying to get that result. And with that, so basically this model now can be used also for other process improvements, since we're confident that this is good enough to represent the small-scale model. So with that, so this is one part of the using first principle model. Then the other part that we're doing is basically using computational fluid dynamics. This goes more into the area of, again, also tech transfer, but now looking at other aspects of the process. So shear is important for cells, basically not to stress them too much. So we want to have a good match of the microenvironment that the cell sees at different scales should be the same. So basically just want to match the shear profile within the bioreactor, and we're also sometimes interested in things like mixing time and other things. So for that, we'll use computational fluid dynamics. And for those of you who are, I don't know if most people might be familiar with this, basically the way it works, we start with a 3D geometry, so we get measurements or drawings from the different vessels that we're looking at and the impellers. We do some final element meshing to get a numerical representation of this. We have our additional information about density, viscosity, and so material properties that we can get, and the operating conditions in RPM, temperature, and so on. And with that and the Navier-Stokes equation, we can then approximate the solution to that numerically doing the CFD simulation, and we get mixing profiles, shear profiles, how tracers, basically if you put elements in there, how they disperse throughout the vessel. And with that, we can compare this again experimentally to validate this, but more importantly, we can use this between different scales to match them and recommend operating conditions between different scales. So one of the case studies that we've done many of these. One of them I wanted to point out is basically we have a condition where we have one process being developed on one site on a 200 liter scale, and that should be transferred to another site and scaled up at the same time to 2,500 liter scale. And in between, there's a phase 3 development where we also needed a 2 liter version of that and a 10 liter version of that. So basically, we have this existing process. It's in a single-use bioreactor, so it's a plastic bag, and this should be then normally the bench scales like glass, and the large scales traditionally were with stainless steel, but lots of the industry is actually moving to single-use bioreactors. So there are different kinds of bioreactors basically, and what you see here is basically a 3D representation of the vessel. These are the this is Russian impeller, this is pitch blade impeller, basically have this model in there. And then we want to have set the RPM for these to have similar shear profiles. And the question is like what RPMs to choose here to reduce cell damage and basically try to keep the cells as happy as they were in the 200 liter scale. So what we found, so basically the first recommendations that they were originally suggested, the people that work on this, basically you had a 2 liter. So basically if you look at the shear profile here, it's hard to say, basically the red areas are high shear regions, which you're trying to avoid, but you usually, especially around Russian impellers, you always have some areas with high shear, but that's acceptable. What you want to avoid is a wide area with high shear profiles. So we want to minimize this and have this as close as possible in terms of overall shear to the original baseline. So the 2 liter actually had too high shear. The 10 liter was still a little bit too high. The 2000 liter originally was actually too low. So we then did a power to volume match between all of them and tried to get a shear profile that's similar to this one, and suggested this one, which led basically to a successful run and now basically use of this 2000 liter bioreactor scale. So this is just a different example. Final part of this is basically to combine these two things together. So basically, in the case where before we did KLA studies, basically to understand the mass transfer between the different for this vessel. But you can also use CFD, basically by simulating the bubbles as particles, how they flow through the liquid, and then get an estimate of the mass transfer from the liquid into the gas from the CFD model. And from that we got a range of basically KLA values over different flow rates, going from the one extreme where everything is really well mixed, so the residence time of the bubble is very long, so we have really good mass transfer, to other assumption basically based on different assumption where just the bubbles were just going up, so the residence time would be very slow, very fast, and that would lead to a very low KLA. So we have that basically range of parameters for our KLA to be able to put that now into the dynamic model as an input instead of the KLAs from the experiment, and come up with basically this required a manual gassing strategy for a longer period of time where we couldn't change it. So we needed to get an estimate on how long it would take to change the oxygen concentration in the tank, and we could use that basically to bound the solution to this and to recommend how to operate this. So this is basically an example of how these kinds of models can be used in situations where you really have limited information about your process and you just have to make decisions very fast. Okay, so this is like basically examples, real world examples of bioprocess engineering. As I mentioned at the beginning, this is the first part. The second part is now turning more to the cell model that's involved in this. This is usually, as I said, usually involves very simple monokinetics for the biological part, but actually the biological part has a big impact on basically it determines what your product is, right? So if the cells behave differently, you will get different product qualities. So my previous work, I've worked on extending or having a more general model for these cells based on what's called flux balance analysis and how this can be used in the engineering setting. So flux balance analysis are also often used in metabolic engineering or biology, where they're quite often, or they're used, but there hasn't been a lot of application to using that kind of information in an engineering setting, in a production or manufacturing setting. So basically what it does, as I said, flux balance models, I'll go into more details, basically represent the biological part as really detailed description, and then that is being incorporated in something that's similar to this overall dynamic system that describes the bioreactor and the system around it. So metabolic network analysis is basically, it's a growing field. If you look at so you can use, one way of doing this is basically genome scale network reconstruction. So you basically start with a genome, and from that genome you look at all the possible chemical paths or reactions that could happen based on the things that are being expressed, and you start building out a huge reaction network, and then you use prior information from existing networks or experiments or something else to cut this or shape this in the form that is representative of the metabolic network or the organism of interest that you're trying to represent. These are huge, few thousands of fluxes or chemical reactions. They are very detailed and can be used for metabolic analysis if you want to suppress one of the pathways to get some different behavior. You do that, and then you do the gene knockout and then implement this to get this. So this is used for metabolic engineering, and there are lots of these available. And then flux balance analysis is basically one form of solving this kind of internal model of the cells. Okay, and just give you a demonstration of how this works. So basically, what you have this is the extracellular environment, this is the intercellular environment. What it does is basically you have different nutrients that are being absorbed by the cells. So you have fluxes going in. Then you have some metabolic network, right, where they're being produced, and you have some product of interest or a waste product, and you have some growth, basically, where the cells use the metabolites to reproduce themselves. So you have that, and if you want to represent it mathematically, basically you can represent it as an undetermined system of linear equations with some bounds which account basically for the reversibility of your reactions, if they're reversible or not. And to solve this, because it's undetermined, you can solve this either by doing experimental validation. So instead of you can measure exactly a few of these fluxes to get a determined system. The other way of doing this is basically assuming some optimization function which solves this. Basically, in the simplest case for bacteria, it usually tries to find of all these possible combinations of fluxes, it will try to find the one that will maximize its growth, right? Or the one that maximizes its growth over time will be the only version of the cells that will be available, will survive at the end. So this is for bacteria, basically a non-constrained environment. This is a good assumption of how these fluxes will be used. So that will give you basically a linear optimization problem as a representation of your intercellular or of your metabolite. So again, we can use this, and we can use this linear program, it's like thousands of variables, and as a model of your cells. The nice part about this is that it's very flexible, so it can change. Basically, if you change your inputs or your constraints, it will react differently because it's an optimization, so it will find the best possible solution given the constraints. So if the constraint changes, the solution will also change. And we incorporate this linear program into the mass like we have seen from mass balance and liquid gas transfer and so on, which will give us a dynamic system where the right-hand side is now a solution of to a linear program. So basically, if you want to simulate this, and people have basically what's one of the contributions, a reliable way of simulating this function. Every time you evaluate the right-hand sides to simulate your ODE, you have to solve a linear program. And if you choose the wrong point, your linear program becomes infeasible, then your integrator starts to behaving weirdly. So you have to go around finding ways of doing this. So basically, it was one of the things that worked on basically finding a reliable way of simulating this. And now you can do this in MATLAB fairly easily. So just to show you why this is powerful, or why this is really useful to do, because you can go around these constraints that you actually have to specify a priori what kind of different behaviors your cell has in different environments. You just include this is included in the model description of this. So simple example is an E. coli fermentation. So basically, E. coli can use glucose and xylose as sugar source for growth. First, use glucose before xylose if it's available. So this is one of the metabolic network constructions that are commonly used. It's not that big, 600 metabolites, 900 intracellular environments, fluxes. And the dynamic simulations of the mass balance from bioreactors is basically glucose, xylose, ethanol as a product, and the biomass itself. We assume that oxygen is being controlled by some feedback controller, so we'll just assume that it's constant. And the input, so basically uptake rates, the uptake fluxes are modeled by mechanisms, which just means that if glucose concentration goes to zero, the glucose flux potential of taking glucose up will also go to zero. What you get from this is basically you get this behavior where, so your glucose concentration here in green goes to zero because it's the preferred carbon source, while your E. coli has an exponential growth phase in this part until it reaches zero. Then ethanol production is going up, and xylose is basically untouched during the whole time because the E. coli doesn't like to use it. And because the linear program also basically, based on these constraints, the solution to the linear program will choose to uptake more glucose than xylose until it reaches this point. So where the carbon source basically changes, which is basically a change in the optimal solution of your linear program. And from there on, basically, because this is going to zero, almost zero, xylose is now being consumed, and your growth rate, first of all, changes, and basically the rate of ethanol production also changes. So all of this is just incorporated into one consistent model based on this solving linear programs. So what we've used this for is basically, so again, I'm jumping around different cell types, starting off with cell culture, so Chinese hamster ovary cells. This was an example for E. coli, and this is now algae, but the same principles. By basically, there's an existing metabolic model for Dunaliella salina, and the goal of that project was basically to have to optimize the production of beta-carotene, which is a nutritional supplement, relatively expensive at $1,000 per pound. And it can be easily produced. Basically, all you need is your algae and sunlight, and once it basically has too much sunlight or too much light and not enough nitrogen, it'll start goes into this starvation mode and produces high concentration of this beta-carotene. So basically, you want to drive this towards this situation where you have a lot of beta-carotene, but at the same time, you still want to have enough algae at the beginning to produce the beta-carotene. And again, it's the trade-off between biomass and your product of interest. And the goal is now, so this is a little bit of an extension, basically, we can do this, so we can do the whole flux balance and then have another environment where we have an accumulation, intracellular accumulation of beta-carotene. And we can use this basically in optimization settings where you do the whole simulation and try to optimize it's sort of a dynamic programming approach where you optimize the input of light and nitrogen source. So we do the same simulation. This is now a genome scale model with a few thousand fluxes of this Dunia salina with all the different sub-parts of the model, including the chloroplast, which has the beta-carotene flux in there. So these beta-carotene, so the product of interest is produced in the chloroplast. So we need that model to represent the production. If we do, so this is again the model calibration. We do simulation of this over time. We can see that basically, first of all, we are nitrogen limited at some point, and then at some point we're light limited. Basically, because the biomass is growing so much that there's not enough. There are a lot of cells, and there's not enough light for all the cells, so they're more light limited than nitrogen limited in this unlimited environment. You can see this again, this metabolic shift as you've seen for the glucose and xylose. This is again represented in that model. And you have your typical growth rates, and you have your chlorophyll concentration, which is connected to the beta-carotene. That we also want a model that matches pretty well with the experimental data. And then we can do this model validation under different conditions. So we've done this in low light, high light, so basically high light, very high. So this is light stress conditions, this is normal conditions, and then this is light stress and nitrogen stress conditions. And this looks just off because it's on a different scale. But otherwise, it's a relatively good model fit. And given that these are actually real experimental data. And so after we've identified all the parameters for this model, we've done an optimization of the light intensity profile and the nitrogen feeding rate to actually be able to increase the beta-carotene fraction of this algae by more than a factor of 2 with this particular profile. So yeah, this is just what's an experimental study just to develop that they can use this kind of models to do this. I guess that's it. So basically what I wanted to show you today is that there are different system engineering challenges in bioprocess engineering, and there are lots of potentials also for having that kind of approach because the challenges are between scales, are systematic in a lot of ways, and model-based approaches can actually still go a long way to make improvements in this area. And then one of the, I guess, future or continuous research in this area would be to get a better understanding of the biological part, to develop more sophisticated models and make them more usable in these industrial applications. And with that, thank you for your attention. Happy to answer any questions.
So, yeah, now we have 10, 15 minutes for questions. So we'll start with Abhishek.
Hi, so I was wondering, is there any significant problem of producing these compounds in a synthetic way rather than just using biomass to cultivate that? Why can't you produce them in a synthetic fashion?
The drugs?
Yeah.
Because they are enzymes. They're like 100 times bigger than the normal drugs that you get. They're very complex, they're very finicky, they don't fold the right way, then they don't have the same efficacy. Yeah, they're just tailor-made basically for a specific purpose. So we're not in the, or at least as far as I know, not. It's still far away from synthetically producing these things.
How widespread now is using the simulations in industry? I worked at Regeneron for 3 years. My project was actually joint with Sanofi. But they were, I mean, this was a couple of years ago, but they weren't quite at using simulations yet. We did some jump, like DOE type things,
yeah.
but I was just wondering at this point how widespread is using these simulations across the MAB producers?
So I think the first principles, they're not very few. I don't know if anyone in the CFD, there are several groups. I've been to conferences where people have produced, shown their CFD results to do P/D matches and other things. So I think it's still not very common, but they're enough. There's probably in larger companies at least, every larger company has at least one CFD group at this point. Yeah, first principles, I haven't heard from anyone doing that.
Yeah, I mean, it makes sense to use it, but I guess when your platform is speed to clinic, it's not not going to be.
Has there any been implementation towards the modeling of maybe use of multiculture systems that use more than one type of cell in the process?
Yes. So there have been, there have probably been more, I'm aware of a few using this dynamic flux balances approach on biofilms and other naturally occurring consortia of organisms. Yeah. But there's still lots of room to do. Bionome is one of the big areas right now that people are interested in.
So you showed this big model of the regulatory cycles, which have maybe hundreds, if not thousands, of interacting agents. So how would the accuracy of the model change if I remove a few of them? As in, is it possible to, how accurate should the model be in order to get very good, very predictable model of the actual system as opposed to very bad model? And how easy is it to, if I put in more effort to discover one more interaction cycle, would that significantly improve the model, or what's the trade-off there?
On the genome scale, there's a benefit of discovering some key things. I mean, there are lots of people have worked on have been curated from different people over time. So there's still potential probably to do this, but this is more from a metabolic engineering perspective, where you really want to understand what kind of knockout you have to do to get a specific behavior. From an engineering perspective, so running this in the bioreactor, unless it's really a key, one of the key pathways, if you knock that completely out, nothing will go. Obviously, but if it's something that's just marginally related and actually doesn't show up in your bioreactor as a real measurable metabolite, it's probably not going to make a big difference.
For you. I'll piggyback on that, and then go ahead. All right. So, can you speak to the numerical analysis, or what kind of metrics you use when you talk about model validation with first principles models? What is the procedure when you actually do validation or calibration?
It's just usually trying to minimize some squares between model predictions. It's simple.
And what are you using for optimality criteria? I mean, are you just local?
No, just local. Just this is bare bones. Sometimes it's not even that. It's one of those just manually trying to find something.
It's sensitivities.
Yes. Yeah. I mean, part of it is basically also the current model infrastructure is not set up for sensitivity. So it's the benefit of finding optimality is still minimal compared to just having the model and having some predictions that give you a good direction to improve it.
Yeah. Okay.
So I might have missed. What was the objective function for the DFPA?
For the
algae. When you make the beta carotene.
It's still maximizing growth. Yeah.
And
there might be some minimizing metabolic activity in there.
And for that, you were just so there were no knockouts in there. You were just looking at when the environmental conditions changed,
Yeah.
And okay. So CHO. So this is. So I'm curious about integrating the first part of the second part of your talk. So you've got CHO, which is what you were talking about in the first half of your presentation, and that's kind of like the E. coli of the eukaryotic world in the sense of how well characterized it is, and we know more about its metabolism than probably any other eukaryotic cell. You've got this amazing DFBA approach, but the approach you're doing with the CHO cell is relatively coarse compared to kind of like the deep dive you're taking into the intracellular metabolic modeling.
Yeah.
What's stopping the integration of that? How long, or do you see that being integrated anytime in the near future? And do you see, for example, Sanofi taking advantage of this? Because I know back before Sanofi acquired Genzyme was actually one of the industrial leaders in metabolic modeling. They had the most sophisticated bacillocellulose metabolic model decades ago. So is this something that we can plan to see on the horizon? If not, what are the hurdles? What are the obstacles preventing that?
I would like to see it. I think just a matter of resources at this point for basically implementing this and having this as a focus. Again, we're more in the manufacturing, it's still science technology, but we're on the manufacturing support. So a lot of our focus is basically to improve the current processes, and that exercise would be more on the research side. So it's there's benefits definitely from there. Hoping we get there.
Would there be hurdles like from the manufacturing side? Would there be hurdles in, like, for example, getting GMP certification for these types of things? I guess that's getting much more mature technology at that point in time. Or is there a cultural issue? Because I know that there are a lot of, traditionally in the pharmaceutical industry, they don't necessarily look at systems engineering as something that's intimate with the bioprocess engineering. So the
there's definitely room for improvement in terms of having a more system-focused culture on this area. That's what we're there for.
All right, we can take one more question. There's another curiosity in the audience.
So let's say you did the DFBA, let's say you did do a knockout. So at this point, maximization of growth rate occurs because the cell has an opportunity to evolve to that point where it's now all of a sudden you've made a change to the cell. Do you have any idea of what you would use for your objective function at that point, or would maximization of growth rate still be a good objective function?
I would probably be a good starting point, I would say, because again, it's not like it will evolve somehow to that. Not as much as in bacteria, where you have this unconstrained environment, because they're again genetically engineered, but they will still try to fight the genetic modification to still grow. Or the ones that are growing faster will be the ones that you will see later on. But it might not be the best solution. There might be some modification. That's probably also interesting to see what would be a good class function for that.
All right. Well, let's thank Dr. Hoeffner for the talk and making his trip out here. And if you haven't, don't forget to fill out your sheets before you leave. All right. Thank you.